Hello, today we're going to do a little demo about how to implement asymmetric encryption in .NET Core long-term support version 3.1. We're going to do that because we have stuff we want to keep secret. And so one of the ways that we could do that is symmetric encryption. But the nice thing about generating an OpenSSL cert and using that is that we have the potential to regenerate it at intervals, and so we can rotate our security key. And asymmetric encryption produces encrypted text that's a little more challenging. Obviously, you can do the same with symmetric encryption, but I was asked on a forum to show a demo of asymmetric encryption, so we're going to do that. So we're going to use OpenSSL, and you can use Chocolatey or you can use install PKG, and you can get OpenSSL. It's available on every platform worth running. And so we open up OpenSSL and we generate a private key using that command syntax, and the yellow highlighted file is the private key we generate with a bit strength of 4096 bytes, which isn't that bad. All private keys contain everything that you need to also generate a public key. So although we're not going to use the public key in the demo, we are going to generate a public key just for spite to show how it is done. And we're going to generate that in the traditional PEM format. And so we feed in our private key. We say we want it to be in the PEM format, and we want to emit the public key out to the out file of .public. All right. Again, we're not going to use it in this demo, but it is a nice thing to know. So if you ever do need to have a public key that you can give to other people to encrypt things to send to you that only you can decrypt with your private key, then that's pretty easy to do. Here's where you can go and fork the demo up on GitHub. And we're going to show you the incredibly simple code required to do it and comment on some things that are super fun and annoying at the same time. So here's our Visual Studio project, which contains one MS test project, and I put the asymmetric crypto class into it. We're going to start by taking a look at the git bash shell script that uses OpenSSL to generate the private and public keys, as we showed in the slides. So that's pretty easy peasy. And then we have some unit tests that we are going to use to exercise our cryptography library. And as we initialize our class, we're going to go ahead and suck the private key out of the file off of disk. And then your basic unit test, of which I made a bunch of variations, is to take some expected tests, spin up a disposable instance of our cryptographic class, which implements iDisposable, so we're getting rid of cryptographic objects that are in memory as quickly as we can, and we're going to encrypt the text and decrypt the text, and we're going to make sure that what we put in we got out, because although putting in something and getting out something different is fun, as a bit blender it's less fun when you want to stash away some data and then get back the data you want. If we run this test, knowing what we know about that, you can see how this very simple algorithm works. And along the way, I'll point out some things that are useful. Here we have our unit test, and we're going to go ahead and go into this. And you can see the first power tip is don't new up the RSA object. The various arguments of the RSA class are hard to replicate, and the easiest thing to do instead is to use the provided factory method of create. So that's what we're doing. RSA, little RSA is equal to RSA.create. The other thing we need to do, though, is we're going to be passing in blocks of text and getting out blocks of text. And so, but cryptography works on arrays of bytes. And so what we need is a encoder that is going to allow us to give it a string and get a block of bytes back, and then give it a block of bytes and get a string back. And although we could use a whole bunch of different encoders,
The one that is far and away the safest, albeit produces slightly bloated output, is the Unicode encoder because it will support all of the code pages and Unicode variations, UTF-8, 16, and so on. We're going to use the Unicode encoder. The important thing here is whatever encoder you use to take your string and turn it into bytes and then take your bytes and turn it into a string needs to be the same one. So you can't mix and match your encoders on the input and output side. Here we have our constructor in which we go ahead and take our private string that is passed in, and as you'll recall, it has carriage returns and line feeds embedded in it. It's got a header and footer embedded in it, and it turns out that painfully the RSA import RSA private key method wants a block of bytes. And the block of bytes can't simply be converted. We, in fact, have to do some work. And the work we have to do is get rid of all carriage returns and line feeds and strip out the header and footer. So that's what key converter does. And so if we bounce into key converter, you can see we break it into a bunch of lines. We remove the last line and then the first line. By the way, that order is far and away the easiest. And then we take all the lines that we split and we put them back, except this time without the new line, using our good friend the link aggregate function. And what comes out the other end is very nicely single string that's in base 64 format. So we can call convert from base 64 on our newly formatted private key. And you can see the RSA cryptography library is now happy as a clam. Excellent news. So now we're going to take our expected text and turn it into cryptographic trash. And there is the base 64 cryptographic trash in question. And then we are going to decrypt it, hopefully getting back, yes indeed, what we put in. And of course it wouldn't be a test if we weren't testing to make sure the input and the output were what we expected. Very simple method that you can use in your own code uses for your own nefarious purposes. Hopefully this was helpful.